Okay, so welcome everyone. Just a pleasure to have here Elisa. Maybe Elisa, you want to put it in your presentation mode?
Yes.
So Elisa has been working for many years on domain adaptation, and well, recently she's been looking into the use of large language vision models for video domain adaptation. She's been doing research, well, at University of Trento for the past, I think, 10 years or so. And she is now the next program chair of ECCV. So it's a good person to know from this point of view. Well, Elisa, I let you the floor and, well, looking forward to a very interesting talk.
Thank you, Nico. As you said before, my talk today will be about the use of large language and vision model to address a problem that we've been fighting with since some time, that is the problem of domain shift when we are training deep architecture. So I will go directly to the point. So I'm focusing here on addressing the problem of domain shift, as I said before, but I'm focusing in particular on a special task that is action recognition from videos. So we all know that the way we have been typically addressing the problem of action recognition in our community in computer vision is through supervised learning. So we have been training neural network given a large collection of videos and associated annotation. So you see here, for instance, a short video clip, and then our neural network will be asked to recognize the action throwing an object. Of course, as you may all know, this is a very hard problem. I mean, this is one of the hardest problems we've been working with in computer vision. And the challenges when we have to understand what is happening in the videos are manifold. So the first challenge is due to the fact that we are not only dealing with static images, we are dealing with video. So we really need to take into account the spatiotemporal information. So we really need to leverage this extra information that comes from time. And we need to do it also efficiently, because imagine, I mean, if we are designing transformers for video, it's not the same as designing transformers from images. This will imply much higher number of parameters. That means that the second challenge that we need to address is also related to complexity in terms of storage, in terms of computational cost. And last but not least, while for images over the years we've been collecting a lot of data set, for videos we have also been doing the same, but you know there is still some efforts to have a very large scale data collection of video. So for this reason, for video understanding we are much behind than from image understanding. So when we go to the specific problem of action recognition, we know that, as I said, collecting a large-scale large-scale data set annotated with videos can be very cumbersome, especially, as I said, for videos. So whenever it's possible, we would like to also leverage a collection of unlabeled data. So somehow we would like to help our neural network also with data for which we don't have annotation. And this is the main motivation when we talk about domain adaptation, because in domain adaptation, typically we are given training set for which we have annotation. This training set is called the source domain. You see an example here, but then you are interested in learning a model that performs well on another domain that is a target domain for which we don't have annotation. However, typically the training set and the test set, the source domain and the target domain have quite a different visual appearance. Visual appearance that can be different for several reasons. So you may have videos with different illumination, you may have videos at different resolution, you may have videos that has been collected in different environments. For instance, here you see open air and you see videos collected in a gym. And you may have also variability in terms of the movement of the cameras, because maybe you have videos from static cameras in the training and then a video from moving camera in the test. So this domain shift issue is really an important issue when we come to look at videos. For this reason, the community have started to pay attention to methodology that explicitly solve this problem of domain shift in video analysis. Surprisingly, we've been working on this since relatively few years. The first work that we could try to find, when we try to look at the literature on this domain adaptation for videos, were works of 2019, 2020. And the recipe there for achieving a robustness to domain shift was to plug into neural network some attention mechanism, mostly attention mechanism that would align video from the source and the target domain along the temporal dimension. Another recipe that was typically used in these works was also inherited from domain adaptation methods from images, and was the use of adversarial losses to align spatio-temporal features and to make these features somehow agnostic to the domain. So this was a bit what was happening when we started to look at domain adaptation. Beside attention model and adversarial alignment, another strategy that was exploited in previous works was also the use of what we technically call the pretext tasks for unsupervised domain adaptation. So somehow you are training your neural network to recognize the object, in this case, the action of interest, but then you are also plugging into your neural network an extra branch that encourages the learning of domain agnostic features by adding another auxiliary task for the neural network to solve. And one good auxiliary task in the case of domain adaptation for video is this clip ordering prediction. So you are also asking to the neural network to reorder a set of clips along the video. Of course, this method that we're using, the pretext task, we're also using some attention mechanism, because attention mechanism have been proved to be very effective in this area. Anyway, when the take-home message here is that when we started to look at domain adaptation for action recognition, we saw that there were two main categories. One category is based on this adversarial alignment, and the second category is based on these pretext tasks. And then, of course, we asked to ourselves if this was the way to go. But before doing that, we also look a bit at the numbers. Okay, so one important contribution of this previous work was also to attempt to measure how severe is the domain shift in the existing data set for video action recognition. So this is, for instance, is an example that if you take the HMDB dataset as a source domain and the UCF 101 dataset as a target domain, the histogram on the red bar tell us the performance that you will have if you train a model on HMDB and you test the model on the test set of UCF. But then if you are training your neural network on data from the training set of UCF, you will have much higher performance. So somehow this gap that you see in this plot is the gap that is due to the domain shift. Okay, you would say this is not a big deal, right? There are a few points, but that's not true. Because then if you are taking other data sets, for instance, if you are taking as a source domain the kinetics data set that is widely popular, and you are taking then the neural network that you have trained on kinetics and tested on another data set, for instance, this NEC drone, that is a data set collected from a drone of people moving in a gym, then you will see that the network that is trained on kinetics perform very poorly on the action of neck drone. However, if you train a neural network on the same domain, on the target domain, then you will have a much higher performance. So in this case, the gap due to domain shift is much bigger. And here started somehow our journey to try to address the domain shift in the case of videos and action recognition. And we try to depart from, we take inspiration from previous work. We use the same data set, the same protocol. However, we try to depart from the ideas of previous work. And what I will try to show you today is that we found that some of the novel, the breakthrough that we have been observing in our community can be also used in this special problem, in this special setting. In particular, I'm going to talk about some methods that we have defined that are inspired on contrastive learning. We have also been making use of vision transformers to improve our models, and also lately we've been using large language and vision models for addressing the same problem. I'm going to start with a first work that we have published at VACV last year, in 2022. So when we started to look at domain adaptation for videos, we thought that one good idea was to not use the pretext task like the clip ordering prediction, but to use something that could be perhaps more general. And we thought that contrastive learning was an interesting alternative. So we've been typically looking at contrastive learning as a self-supervised feature representation methods. We think that contrastive learning can be used in videos to learn thanks to video augmentation, some representation that are robust to domain shift. But we also thought that we can do something better. We can plug a contrastive loss in order to pull together vision representation from different domains, but corresponding to the same classes, and also to push far apart video representation from different domains, but belonging to different classes. Now there is a problem if we want to implement this idea that looks quite reasonable. And the problem is that for the target domain, you don't have labels. So we need a neural network that also robustly estimate the pseudo labels in the target domain. And this is somehow what we have done in our first work, where we have proposed an architecture that now I'm going to roughly describe. So our architecture takes as input both the source videos and the target videos. Videos are divided into clips. Each clip is processed by a feature extractor, the network that we denoted with phi. And then we have some attention model that performs aggregation of the feature representation that we have obtained for each clip. One first contribution that we put in place is that in order to learn clip representation, we resort on unsupervised contrastive learning at clip level, where basically we have a video of the same clip considered as positive and video of different clips of different videos in the mini batch considered as negative. We end up having some representation for the video of the source and for the video on the target. But then we are not done yet because we design on the top of this a dual head architecture. And the reason for having a dual head architecture is that we want two heads that perform classification in a different manner. But then we also look into some agreement of the prediction of the two heads. And this agreement is very important because if the two heads agree, that means that the pseudo labels that the head estimate for the target sample is a clean pseudo label. So we can really use it for our alignment procedure. So this is a bit the idea. This idea is implemented by several losses that we plug in the neural network. In particular, this is a regular cross-entropy loss on the data from the source domain. This is a supervised contrastive loss that is applied on the data from the source domain for which we have annotation. And then we have some alignment loss among that also operate with contrastive learning, tend to the representation that we have for the source and the target domain. And also we have another unsupervised loss that learn useful representation, not this time at the clip level, but also at the video level. Last but not least, this further loss promoted the agreement among the prediction for the target samples in the, that have no annotation. What is happening in terms of numbers if you use the architecture that I have just presented to you? So basically, we compared our network with the state-of-the-art methods for unsupervised domain adaptation and action recognition. And as you can see, in two settings, when you have as a source domain HMDB and when you have a target domain UCF and vice versa, our approach is the one who get numbers that are closer to the numbers that you will get if you have supervision in the target domain. Again, this data set may be too easy to test what we want to test, so we also addressed the most challenging setting of having as source domain the kinetics dataset and having as target domain the NEC drone dataset. And here the situation is different. So our method is the strongest among the state-of-the-art, but we are quite far from closing the gap, okay, for approaching the performance of this 81.7 that you will get if you have supervision on the target domain. So this stimulates us to work more on this, and we propose another work. This time, transformers started to become a bit more popular in our community, so we decided to change the backbone of our architecture, and instead of using a ResNet architecture and i3D, we were using something inspired by video transformers. In particular, we resorted on the spatial-temporal transformer that you see illustrated here, that was published by Shahir and colleague. And then we designed a method for cross-domain adaptation based on transformers that is roughly illustrated here. So our approach is based on two steps. On the first step, we are basically only using the data from the source domain to fine-tune the transformer. And on the second step, we are performing the real adaptation. So maybe we look at each step. So in the first step, we are, as I said, just using the data from the source domain. And this is a spatial temporal transformer. So there is a spatial part and the temporal part. And we are only fine-tuning the transformer by basically changing few parameters. And in particular, we fine-tune only the parameters of the normalization layers. And we use the cross-entropy loss because we have supervision of the source domain. During the step 2, that is the adaptation step, we are basically freezing the features that we obtain from the spatial transformers, and we are only changing the parameters that we have in the temporal transformers. And to drive this adaptation, we have two losses, a cross-entropy loss on the source domain, and then we have an alignment loss that is derived from an information theory principle that is the same information bottleneck principle used by the popular Barlow twins method for self-supervised learning. Here, the idea is to align representation of the source and the target domain by making the diagonal of the cross-correlation of the feature, the matrix of the cross-correlation among features as much as diagonal as possible. And we figured out that this was actually a good criteria to align representation of the source and the target domain. We perform an experiment of the same setting as before, and as you may see here, thanks to the use of transformers, basically we figured out that this data set is kind of saturated. Still, our method is, I mean, the best among the different baseline. But here, the important thing is that we achieved a much better performance with respect to the previous method when we were looking at the difficult data set, kinetic snack drone. Here we were really having a 65.3 in terms of accuracy on target domain. So we were trying for the first time, we were approaching for the first time the performance of our upper bound. Something also interesting when you use transformer for such task is that you can also expect the values of the self-attention. And for instance, if you look at the network and you look at the frames that the network use, the network that is only trained on the source data, then you may discover that the network to predict an action is not really focusing on the most important frame. But then if you perform the adaptation as we propose, then the network is giving more importance, is attending more to the frame that really contain the action. So this was a confirmation of that our approach was operating in a good way. So this concludes a bit, first part of my talk, where I basically showed you what we got without language and vision for studying the problem of domain shift in the context of action recognition from videos. So we learn two things. The first thing that we learn is that ideas from self-supervised learning for contrastive learning can be also used to try to suppress the misalignment among features from the source and the target domain. And the second thing that was perhaps less surprising was also that video transformers are more robust to domain shift, but still they need to be adapted. So of course they tend to generalize better, but still we can design some clever way of adapting transformers to our domain of interest. Something that we also start to look at was the fact that domain shift is an issue for action recognition in video, not only for action in a 3D dimension, but it's also action in egocentric setting. So it makes sense to study domain shift also in an egocentric setting, and this is something that we have done in the follow-up works. Another aspect that I want you to notice is that somehow domain adaptation makes too strong assumptions. In the classical setting of unsupervised domain adaptation, we make the strong assumption that we have the same label sets in the source and in the target domain. However, as you may imagine, this is not the case in real application. And this gives us the inspiration to try to address this problem of video domain adaptation in a more difficult setting, that is open set domain adaptation. I'm going to show you what I mean in a few minutes. And also we figured out that more powerful models could be also used to address this challenging problem. And so we resorted on a method based on clip. And our method is called auto label, and I'm going to explore, I'm going to show you why. So first, let's look at the setting. So the difference between closed set and open set domain adaptation is the one that you see here. So basically in open set domain adaptation, there is an overlap between there is a subset of classes that we observe both in the source and in the target domain, but then there is a bunch of classes that we didn't observe in the source domain. So somehow we should have a method that is able to recognize which classes are known and which classes are unknown. Why this is important? Because then we can perform some form of feature alignment only for the videos that correspond to known categories. So this is the challenge. So basically, when we are tackling open set domain adaptation, we have this additional challenge of detecting the unknown and target specific categories. This slide somehow summarizes what I just told you. So in OpenSet video domain adaptation, we would like to adapt a model to the target domain, and then we would like to classify a video to one of the known classes, but also we would like to reject the unknown videos, the samples, the videos that belong to the unknown classes. So this is quite much harder than the closed set domain adaptation. As I told you, we decided to look at CLIP as a method to use in order to solve this problem. Why we look at CLIP? So we look at CLIP because we know that CLIP, it's a very powerful architecture. It tends to be robust to domain shift because it has been pre-trained on web scale dataset. And one important feature of CLIP is also the fact that CLIP enables zero-shot classification. However, CLIPs enable zero-shot classification if you know the class names that you want to recognize. So, for instance, in the example here, you can use CLIP to classify a new video as the class ride horse. However, you should know which classes you're looking at. So somehow our challenge here was, could we use CLIP without any prior knowledge of the unknown class name? And the answer is yes. But then you need to adapt the CLIP, and the way we decided to adapt the CLIP is through a method that we called auto-label. So auto-label means that we are plugging an extra component, that is this pink component, into the architecture that is able to identify a set of textual description of target private classes. And then once we have this engineered, designed, this auto-label block, then we can use it CLIP because we have some description of target-specific classes. Now, what I'm going to show you is how we design this pink block. First, let me give you an intuition, okay? So our intuition was that since we don't know these names of target-specific classes, but then we know that typically an action can be loosely defined with three elements: the objects that are happening, that are in the scene, the actors that are moving, and the environment. So somehow our intuition was, given a target videos, we can use state-of-the-art captioning models to take out a set of, to extract a set of attributes from the video. For instance, in this video that you see here, some relevant attributes that correspond to object, actors, and environment could be person, golf club, that describe the object, and then grass and trees. So somehow the meaning of this slide is we can leverage from a state-of-the-art captioning model to extract a series of attributes, and then we can derive some target-specific description from this set of attributes. And this is what actually we did in auto-label. This set of slides somehow summarize how our method works. So there is a first step where we are extracting relevant attribute. We feed for this an image captioning model that was state-of-the-art at the time. In particular, in our work, we use VILT, but if we are using other captioning model, things wouldn't change much, I think. So then we are feeding the captioning model with a video, and then we are feeding the captioning model with a template. And then with this scheme, we are able to extract attribute. Then in step number 2, we are feeding our videos to a video encoder, and then we are clustering. We are adopting a regular k-means cluster to cluster relevant visual features. And then we count occurrences, and we use the TF-IDF method to extract a series of candidate labels that correspond to the videos that we have in the target domain. once we are able to extract some candidate labels for the target domain, then we should have a strategy to match these candidate labels with labels of the source domain. And for this, we use, let's say, an empirical procedure to match labels extracted from the target video to labels that we had in the source domain. This means that we end up with a final label set where we have common categories and labels that correspond to target-specific classes. We are almost done, because once we have obtained this final label set, then we can use the regular clip and reject videos that correspond to unknown categories. We tried to benchmark our method against state-of-the-art methods. So here you see that the different methods, here the performance are measured with the different metrics that should somehow take into account the fact that this time I am addressing the open set domain adaptation problem. And we compare our method with different set of methods. So previous methods that were using ResNet 101 as backbone, and then methods that were using CLIP as backbone. In particular, one finding of our paper is that if you use the action clip model and you especially embed the action clip model with an heuristic to reject samples that correspond to the target private classes, then you would achieve good performance, but you wouldn't achieve the best performance, because the best performance are the one that we achieved with our proposed strategy auto-label. A similar finding we had when we also consider the reciprocal setting from HMDB to UCF. And also we tried our approach on the Epic Kitchen dataset. As you may see here, all the methods perform much poorly. In particular, CEVT, that was at the time a state-of-the-art method for open set domain adaptation that we applied to videos, and by using the ResNet 101 backbone, this was really, really poor here. Action clip, so simply adapting clip to this new problem, it's already producing better numbers than previous unsupervised domain adaptation methods that were not leveraging language. However, if we are using our auto label, there is a huge boost in terms of performance. So I'm going through the main take-home message of this first work. So we were the first to try to use a clip-based framework for addressing the problem of open set unsupervised video domain adaptation. Clip is already quite powerful because it has already zero-shot capabilities and has been trained on the very large-scale dataset. However, thanks to auto-label, we are able to enhance the capabilities of CLIP. One also interesting finding of our work is that we found kind of beneficial to describe action by attributes, and for this we used captioning models as a way to extract these attributes. The last work I would like to present is a work that we've been presenting at ICCV the past month. So this is still on the use of CLIP, but this time for addressing another setting on video domain adaptation, that is source-free video domain adaptation. I'm gonna show you what I mean by source-free domain adaptation. Traditionally, in domain adaptation, as we said before, we have source data and target data, and we have annotation only in the source domain. But in source-free domain adaptation, we assume that we are not given access to the data from the source domain, but we only have access to a source pre-trained model. And then we would like to adapt this model in order to perform as much as possible well on the data from the target domain. So this is a much more challenging setting. And the question is, can we leverage language and vision for that? Our intuition for this work is described by this image that you see here. So what people in the community of domain adaptation has been doing for addressing source-free domain adaptation is to fine-tune in a smart way the model trained on the source data, thanks to the target data, by having some form of unsupervised and self-supervised loss. So what you see here is the traditional approach that we adopt in source-free video domain adaptation. However, this approach has an issue because maybe some useful knowledge that we had from the source domain can be overwritten if we fine-tune the data on the target domain with the self-supervised loss. So we don't want that, right? Another alternative that we have is to use a clip in a zero-shot fashion without training. So by just, freezing the vision encoder and the language encoder and seeing if, if the model can be already powerful for the task at hand. However, this also has a problem because in this way we are not leveraging any useful domain-specific information, any information from the data of the target domain. We are just relying on the ability of clip to generalize. So the method that we propose is somehow the best of both worlds. So we would like to leverage the complementarity of clip and the the other approach that somehow perform adaptation thanks to using the target data. And we did that by simply learning an adapter. So in this few slides, I'm showing you the intuition behind our design of the architecture. So we are basically performing a first step when we are training some adapters. And in particular, we are training two adapters, one adapter for the source domain and one adapter for the target domain. This is a classical design of methods and networks like action clip that operates on with large language and vision loss. The only difference here is that when we train the adapter on the target domain, we should resort on some pseudo labels. And in particular, we obtained the pseudo label with this network. The main contribution of our work is not just training the adapter, but it's actually designing this ensemble distillation, where basically we produce a final neural network that operates within a teacher-student scheme. And in particular, our network, that is the student, is trained thanks to three teachers, a model that is obtained by training the adapter on the source, a model that is obtained by training the adapter on the target, and a model that is simply obtained by just using clip of the shelf. This is a bit the results. Here, the number of baseline is higher than than for the works that we've seen before, for a reason that the number of methods for source-free domain adaptation are many now. And we can have a look that, so if we are already applying a clip with a different backbone, this network is already powerful and generalized quite well for source-free domain adaptation. So it's already approaching the upper bound somehow. If you are using traditional methods for source-free domain adaptation that don't use language, this method typically perform much poorer than zero-shot clip. Our approach is somehow the best because it exploits the best of both worlds. This is especially evident in this other benchmark. This daily DA benchmark is a benchmark that has been defined specifically to test the problem of source-free domain adaptation in videos. And our approach is outperform the best competitor that doesn't use language, and also outperform a zero-shot clip. So for this second word, the main take-home message is that we were able to design a novel but simple approach for source-free video domain adaptation. I consider here simplicity as a clearly an advantage, our method is obtained by combining complementary information that are derived from domain-specific, target-specific models and from CLIP. We extensively evaluated our methods on benchmark, and in particular, previous work have introduced a specific benchmark to test this problem. I will conclude my talk by showing you this plot. So this is what has happened over the years by considering the adaptation problem for the daily DA dataset. So we have a regular approach for unsupervised domain adaptation that are these yellow dots. And then we have approaches that consider specifically source-free domain adaptation. They are these red triangles. And you see that over the years, we have been having performance that are not especially satisfactory. And if we have approaches like this external or this ATICON that are approaches for source-free domain adaptation, but they are specialized for videos, then we get something better. However, these approaches are already outperformed by applying clip off the shelf. And in our work, we have demonstrated that is it possible to improve further by taking the best of both worlds, by taking intuition from external and taking the generalization capabilities of CLIP. Now the question is, with this, thanks to the use of language and vision model, did we solve the domain shift problem? The answer is not yet. The upper bound in this dataset is still 61. And in other dataset, this is even more severe. So I think we can still work on this and try to leverage language and vision model for improving the generalization capabilities of our action recognition network. In particular, I think we have a lot of opportunities by exploiting, for instance, captioning models. So we can use better approaches to describe what is happening in videos of the test domain, of the target domain. Something that I find also interesting is that domain adaptation is perhaps a setting where we have too many assumptions. So I judge a bit more interesting to study the problem of domain shift in a domain generalization setting. So when we assume that we don't have any knowledge on what we are going to see at test time. So I think this will be much more important, and I think we are ready for this next challenge thanks to the help of language and vision. Last but not least, all these works that I've been presenting to you and other works in the literature do not consider at all the fact that this model is becoming huge. So I think it's also mandatory that we start to address on the ability of our neural network to generalize, but also the ability of this neural network to improve their efficiency. This concludes my talk, and I would like to thank you for the attention. And this is also, I would like to thank my collaborators in this project. Thank you very much.
Thank you, Elisa. So, well, I'll invite people to ask questions. So, just to break the ice, I'm just curious about your title because you talk about the unreasonable effect of large language model. But actually, in your talk, you have just, demonstrated that it's reasonable that these language models are helping us, and we can definitely use them.
This was a long discussion when we decided the title of the paper, because I see this in this way. On the other hand, my co-authors stated, and I can see their point, is that CLIP has not been trained at all for videos, okay? So this is a simple application of CLIP without, anything for specific for videos. So that's why we end up using unreasonable as a word.
No, but this is definitely provocative. So it's good for the reviewers. When you see it, it seems, wow, that's something that I need to read. No, it's definitely a good marketing strategy on this. Well, I see a question from Sergio. So Sergio, maybe you can ask the question directly. You put it in the chat. Otherwise, I can read it.
Okay. Can you hear me?
Yes.
No, I was just wondering, making almost a parallel between conventional classification of images and object localization in images, where you've got many different objects in the same image. Whether there's any progress yet on dealing with actions that are happening in the same, multiple actions that are happening in the same video. So when because I think all of the examples that you've shown, we have one action in a video, like the golfer or whatever. But how would you approach a problem where you might have multiple actions, including unknown actions, in the same video sequence?
Yeah, this is a difficult question. I mean, I think some principle could be also leveraged here. However, I don't think a naive adaptation of what I just showed you will suffice, because I mean, what I think is that captions can provide a lot of information on what is happening in a scene at global level. Okay, so I think creativity on how to exploit caption could be a way to go. However, if we simultaneously want to address this together with the problem of domain shift, it's not trivial to me to combine some holistic understanding of the scene, obtained maybe thanks to captioning and thanks to visual features, and a strategy for adaptation. It's much more complex tasks. I will have to think. Okay.
But what about doing some kind of, parsing of the video? So you could always try to build, okay, they are happening at the same time, but you can also localize where the action is happening. And you can also try to say, well, also using the language model to say, well, in this side, it's happening this, in the other part, it's happening something else.
Yeah, no, I agree, but still, the much of the community working on this, even how to exploit language and vision for action localization is something where we are working on, but I would say we don't have a stable solution yet, right?
Absolutely. Okay, other questions? Guys, don't be shy. You are quite a few of them. It's hard to believe that you don't have any.
Okay, I have a quick question. Do we know what are the training data of clips? So because clip itself has already good performance, so does it already contain some target knowledge for your domain adaptation task?
I mean, the video that we are using, this is the AIDA. This is and also UCF HMDB. They are video of sports. So it's not unlikely that clip have been digested similar data. So this can be part of the reason why it's effective. This is what I was saying a bit before. Still this has not been trained to to handle temporal information. No? But yes, of course. I mean, the reason why it's effective is probably it has seen something similar. This I agree. I mean, and actually, this also maybe give us a chance to reason on the fact that the works that have been presenting to you and also other works from colleagues working on similar problem, we are still using data set that at this point are not competitive anymore. So maybe we are ready to study this, you know, in other settings too. However, we have also numbers for Epic Kitchen, and as you may imagine, numbers are lower, right?
But should you
Okay,
have some
thanks very
some
much.
sort of fine tuning that you can do? So if you know what sort of actions you have in the video, maybe you can probably do.
No, we can. The adapter
Yes.
is serving for this point, for this need. I mean, the principle is that we also want to measure what zero-shot clip can do in a training-free fashion.
Okay, there is Junaid.
Can you hear me?
Yes.
Yes, okay. I have two small questions. They're interrelated. For example, in the videos, the span of activity is more like same, or is it differ, and how your proposed approach behave on different outputs? Have you done this kind of qualitative analysis? If the span of activity is longer or shorter, this affects the output?
Yes, these are facts, but we didn't evaluate this well properly, in a sense that we've been using you know, the same clip that this time not clip language and vision, but I mean
Okay.
the duration of the video clip that other works were using before us. So I would say we didn't really study this in detail, and it's an interesting suggestion. We should have done this. But
Just
I'm not able to answer because we didn't run experiments. We've been using the same data set that other people were using with the same protocol. That means that this dimension of length has not been sufficiently exploited. Sorry for that.
Just an addition, all the dataset which you mentioned, is there any particular dataset that you can suggest for this kind of study?
I mean, we took this paper as a reference. This was a paper that was presented at ECCV last year, and they were already introducing two datasets for the task. So this is where we started.
Okay, thanks.
So if you look at the reference, then you will find their web page with the datasets.
Oh, thank you.
Okay, anybody else? I'm just curious, Elisa. Okay, so since we do of course the zero-shot clip and so on, but can we just apply the same stuff for domain generalization?
As it is, no, because we are in a sense, in principle, we can use some ideas for targeting the scenario where we don't have target information, but the way we are using the network now, no, because we are really fine-tuning the adapters also on the target samples with pseudo labels for the target. So we really need to redesign this for domain generalization. But of course, I mean, there are already works. Also, there were some works at ECCV about generalizing the generalization, for instance, in the egocentric vision. So I think this is an interesting direction. Yes.
No, that's why I was thinking in a particular domain, maybe you can start doing it when you have some extra domain knowledge somehow, maybe implicit in some way.
Yeah. I mean, there is a paper from University of Bristol where they studied the problem of generalization in egocentric setting.
Sergio, I see that you have another question.
Yeah. First a comment, a cheeky comment. It's just to to assure people who are in the audience, who are young researchers, students, that there's plenty of things to do. So don't worry, you've got a bright future. And the other one is, Elisa, I was wondering whether there is applications for anomaly detection in your work.
We are working on that.
Okay.
So we are working on large language and vision and anomaly detection on videos. So this is something we hope to publish soon. So I think it's an interesting and what I can tell you is that we found some benefit in applying language and vision to anomaly detection. We don't have a solid method yet, but we hope to publish soon.
Okay, thank you.
Okay, so well, let's stop here. Thanks a lot, Elisa, for everything. So virtual clapping of the hands from everyone. And well, I think it's an excellent you know, domain. And as Sergio said, there is still a lot of you know, work for everyone. So okay, thanks a lot for everyone, and well, looking forward to the next talks. Thanks, Elisa.
Thank you. Bye. Bye.
Thank you. Bye bye, guys. Thank you.
Bye bye.
Bye bye.